will briefly illustrate the link between these neurodynamic concepts and embodiment in this little section that completes the core lecture I gave yesterday. And so it's really about how to link these fields to time-varying sensory inputs, and also how to control the a motor system with that, and ultimately to act in the world. That's the point we always emphasize. We'll come back to that in the last lecture, where we think about that more globally under the label of embodied cognition. Now, the linking to the sensory input is actually kind of trivial. It just illustrates what we did. There is a special problem that needs to be addressed when we link to the motor system that I hinted at earlier. So I'll use a robotic demonstration that we did. That this is the part of the doctoral dissertation of Estela Bicho, who's now teaching in Portugal. She did that in Marseille. We built a little robot then by hand. It's a terrible experience dealing with hardware. Never again, I promised after that. Today, you can buy these kind of robots. At the time, it wasn't so available. This is a PC on wheels. There's inside a PC, which at the time was considered to be a really embodied computation, somewhat challenging. Now it's very easy to obtain that. So there are two motors here at the bottom that are servo-controlled motors. Here's a schematic. So this is a robot that can turn on the spot. So it doesn't have any problems like a four-wheeled car with parking and so on. It can turn on the spot. So it has 2 degrees of freedom, but can achieve any position in the plane and any orientation, the so-called non-holonomic motion planning problem that I'm not going to get into. So for the current purposes, the sensors that are interesting about this robot are microphones here at the top. These were very cheap, simple microphones. I'll illustrate them in a moment. And the robot was designed to follow sound sources, very simple kind of behavior, phonotaxis. There are other sensors that we use for obstacle avoidance, and the robot demonstration I'll show you actually has obstacle avoidance, but I'll not explain here how that works. It's actually in the book chapter 4, there is an explanation of that part as well. And this is published work, all of this. So the sensors are really just 5 numbers, right? 5 microphones that have 5 intensities of sounds they measure. And we take these 5 numbers to drive a neural field. We drive the neural field by creating artificially some kind of tuning curves that give different amounts of activity of input to neurons in a representation of orientation, which is called heading direction for these robots. And these tuning curves are sort of roughly modeled on the sensitivity count of those microphones. So those microphones have some angular sensitivity, about plus minus 30 degrees, where they get most of the sound intensity from. And we model that by these curves, not very precisely. And the cone isn't exactly Gaussian in shape and so on, but it's a good approximation. So the input to the field are these 5 Gaussians. And the amplitude of Gaussians is the loudness that we measure. And so a field will be defined over heading direction that will define then movement targets to head to. And that field will receive these 5 Gaussians as input. And the idea would be, for instance, if you have 2 sound sources, then microphones, for instance, close to the source might get more sound. So the Gaussians are multiplied with a larger number. Maybe there's less loudness at this from this source, multiplied with a smaller number. The superposition of those will provide input to the field. The field will generate a peak when it decides that there is significant sound in the environment, and that will be a representation of a sound source, and then you can navigate to that location. So here are a few illustrations of doing that. This is the robot just standing in a certain place. We disconnect the motor, so it doesn't actually turn, it just listens. And here on top, you see these 5 microphone Gaussians superposed as a representation of its input. So this is over heading direction. There's a source, which is just a loudspeaker, and that loudspeaker is playing music. We always used Vivaldi because of its high, the seasons of Vivaldi has these high violin frequencies that these cheap microphones react nicely to. What we actually did very hands-on experiment, we had this music and we just turn the loudness knob on the amplifier up. So this is what happens here. It's ramping up in time of the loudness of from the speakers. And as you see, there's a detection instability happening here at this moment, at that loudness, which is a little later than where we first see the signals. And then it gets stabilized. You see it suppresses activation somewhere else. So this is now a stable representation. You see it's sort of a noise reduction, compressing the fluctuations by this self-stabilization nature. And it's a good estimate of the direction in which the sound lies. Here you see a demonstration of the fact that the field can do selection decisions. So we had two loudspeakers in two locations, or here, two locations, far enough apart to have a bimodal sound distribution. And just by chance, the system selects this sound source initially, and then has a very stable peak centered on this sound source. You see the volume of the second sound source actually is a little higher here in this later phase, but the selection is very stable, very clear. So it doesn't come anywhere near selecting the other one. And you will see in a demonstration later that that can actually really happen. For instance, it happens often that there would be some reflection of a sound source in the, from like an echo, and you have to suppress that echo. In fact, the practical engineering manifestation of such selection decisions is robust estimation. So here, for instance, what we had is one loudspeaker, but we had a cardboard neighboring or on the side of that loudspeaker from which some echo arrives, and therefore you have this very asymmetrical distribution of input overheading. And robust estimation would try to eliminate the influence of these remote estimates from our estimate of where the source is. So to sit on the local maximum, which is exactly what the field does. So the inhibitory interaction over longer times acts like a robot estimator. That is, once the peak has been established, it will position itself in a way that then ignores inputs that lie outside the range of the peak. And so in a convergence process, it will lock onto the local maximum, which is what robust estimators do, for those of you who know how engineers approach robust estimation. This is of course all dynamic and continuously linked to input. So if you move the sound source, the representation of the sound source tracks that movement. It tracks it in with a little delay, which is not visible here because of the time scale of the dynamics, which needs some time to relax. There's some subtlety about that if we can actually minimize that delay, but maybe I won't go into that. And finally, we actually even created working memory on this system. The original idea was to have a human voice call that robot, and the voice would, so that you don't have to speak all the time. The voice would be intermittent, and it would store the memory of where that sound source was. We later replaced that by music, because it's very boring to speak to that robot. Doesn't understand anything, just looks for your sound. And we played this music instead, and that music is intermittent, so it was so useful to have that memory. So here, technically speaking, the memory is really just a very small thing. Here's a sound source that is turned off, and this is the peak while the sound is on. And here, this peak here, that is the memory. See, there's still a peak, suppresses the neighborhood. That's the working memory. In this robotic demonstration, we actually had a process that actively turns off memory. So we did that by lowering the resting level as soon as we detected that there was a peak without input. We had some peak detection mechanism that we'll see again later for that. And we did that because if you think about heading, if your robot moves around and it is going for a source that was only perceived based on memory, then the estimate of where that source is becomes invalid after some time, because the heading would change as you move around. So you don't want to keep that in memory forever. So it was sort of a demonstration of that principle, how in principle to do forgetting as well. As you know, forgetting a nervous system is actually a complicated issue. So that's the different dynamical modes in that field. And now we can think of how to actually make the robot move based on that. So what we want is the robot to head in the direction that is indicated by where the peak is, the heading direction of the peak. I've sort of glossed over a question of heading direction being in which reference frame that is, and I'll come back to that in the next lecture, which is today. So that's sometimes called the readout problem, right? A lot of connections networks, for instance, have a readout element in that you're looking for which neuron fires most, for instance, and then you're saying, I will decide for an estimate or for whatever the network represents to take what the winner takes all, the winning neuron stands for, codes for. There is a problem with that, doing that dynamically. And that problem is sort of a normalization problem. And so if you, so the theoretical way of thinking about how to determine that peak, if you don't do this by the algorithm, actually state of the art is a lot of people do this by an algorithm. So some argmax, and that's of course not neural at all. It's just from the outside. If you want to do all of that consistently in neural terms, neural processing terms, you have to understand how that could be done, and it will be done by mapping, right? By taking the neural activation, and this neural activation has some influence on the motor system that you express by some neural activation being sent down there. And then you have this normalization problem. It's a well-known problem in computational neuroscience. So you can think of this mapping as a theoretical mean. So you would say every location votes for its value. So for instance, this location votes for this value along the dimension, and this is its weight. If this was a probability density, you would just say it's a theoretical mean. That is, you would take the suprathreshold activation, it's a positive number, and you multiply the position where that activation is with that probability density, sum over that, and then you would get the theoretical mean. You only get that mean if you normalize correctly. So if the sigma u of phi is a probability density. Now you can see that if you don't normalize, let's say if you just rescale the peak, make the peak a little smaller, then all the numbers in this top term become smaller. So your peak will be more to the left, right? Or if you have more activation, you blow up the peak, all the numbers become larger. So your estimate goes to the right. So the peak, the theoretical mean will be only correct if you have a normalized peak, right? And so in neural networks, this shows up as the level of activation matters when you want to have every neuron vote for something, because if you give all the neurons more votes, that's going to distort or bias the estimate. Now there are some proposals in the literature how to do that, multiplicative, divisive normalization, quite complex. There are some claims that neurons can do that. The obvious problem is what happens when you don't have a peak. When you don't have a peak, you divide by 0. So normalization is not an operation that is robust under removal of activation. And so if we want to do all of this autonomously without any external observer detecting whether there's a peak or not, we need to deal with that. And it turns out the answer to this problem is insightful and is something that is pervasive across the nervous system. And to address that question, I briefly have to introduce the notion of behavioral dynamics. In other forms of the school, we actually spend a whole time on that. And if you read these background chapters, there is some deepening of that topic there. And so how we actually achieve for the robot to do any action is actually by creating a dynamical system that makes the robot perform. Let me explain in concrete terms, and you'll see that's a very general idea. So for instance, if I know where the target lies in the world, here's the coordinate frame, this is the robot, right? And what we call heading direction is always to some external reference. So here it's an arbitrary axis, this axis here, let's say your north or your south or whatever it is. And the orientation relative to that axis is what the heading direction is. Turns out it doesn't matter what that axis actually is. You don't need to calibrate it because only differences between headings matter. So if you measure the target relative to that same axis, see the distance that matters is this angular distance between the current heading and the desired heading. And so the calibration of these individual angles doesn't matter. You can have some offset, doesn't matter. So to make the robot head through this target, all you need to do is create a dynamical system that now has as its variable not activation, but heading, this physical thing, the heading of the robot. And so dynamic system of heading means you have the rate of change of heading, that's the turning rate of the robot, against the heading direction. And you want an attractor, a fixed point with a negative slope, at the heading that is the desired heading. So at phi equals psi. So this would be where the psi of the target lies, has a negative slope as an attractor, right? It's in practice, it would be a periodic function because it's an angle. So here, so it could be a sine function, for instance, or some, actually, we'll see in a moment how we construct it. And that's how we will actually generate the behavior. That is a very general principle. I hinted at that at the beginning, that when you create behavior, you have actually physical dynamics of the physical thing itself, the robot's inertia and the physics of that. But any engineer will know that you can never really achieve anything physical without dealing with disturbances. One of those motors doesn't exactly what it's supposed to do, or there is some fluctuation in the current or in the circuitry, or in the sensors, for instance. And what you need to do is to counteract these disturbances, certainly not allow disturbances to accumulate over time, and even counteract those to compensate for those so that they don't matter over time, they decrease. And that's, of course, the topic of control theory. And this is essentially a control theoretical kind of thought that is used, however, here for planning. That is, we're saying we have a desired state, and the deviation from the desired state is regulated to zero by this kind of dynamics. This would be called a P controller, a proportional controller, if you were a control engineer. And so this is very pervasive. If you think about muscles, for instance, and how muscles achieve desired forces or torques, then they have a P controller built in, which is the stretch reflex that actually makes that the muscle length, when it deviates from a set point, the reflex actually brings the muscle back to that length. Muscles only act in one direction, so you need two muscles for the two directions, but together they do that. So if you take that into account, then you recognize that you don't really need to read where the peak position is. What you need to do is erect an attractor at the location where the peak position is. So maybe, if you were to write it down, maybe you think you still need the specified value. I'll show you in a moment you can do that without knowing where the attractor exactly is. And in particular, that means if you don't have a peak, what you want is just a contribution to this dynamics that is flat. So it's critically, it's marginally stable. So the slope of this dynamical function goes to zero. And so what you want to is to control both the position and the slope of the position of the fixed point and the slope by that peak. And that can happen in a very simple form. I wrote down here the solution to that. So for instance, if again, unfortunately, I took here X rather than phi, I should correct that. So this is supposed to be this heading direction. So this would be a mathematical form to write this down. If I knew where the peak position was, the specified value, I would put that in here. And then phi minus that with a minus sign, that will be a negative slope that has a zero crossing at phi equals phi peak. That will be the appropriate function. And that slope, that's the genius strike here. The slope I will choose to be proportional to the entire probability mass here under this peak. So the sigma of phi is the positive part. I see there's a parenthesis missing here. It would be under the positive part of the peak. And so summing over that, that's the area of that peak. And by multiplying that area here, I make sure that when there is no peak, I multiply with zero, then I get this. Right? So this formula actually does the job of creating an attractor when I have activation and creating the flat case when I don't. Now, if you insert, I think I have this, maybe I don't have this computation here on the slide, but if I insert the formula for phi peak, then you will see that the denominator cancels. Remember here, the phi peak is the expression where phi is under the integral here on top, divided by just summing. I introduced phi prime just to say it's a different integral, different variable. So an integral over just the mass, right? This term, and that's exactly the term I'm writing in front as a slope. So when you insert this expression into the equation, insert this into this equation, you get two terms. The first is where phi is multiplied with that term, and I have put that here at the bottom. Here, this is this term here, phi multiplied with that integral. And the second is when there is a similar integral here on the top, and then I have the denominator is exactly this thing that cancels. And so the integral on the top is the sigmoid multiplied with that variable you're integrating over phi prime times d phi, right? Yeah. So actually, in this case, I put a prime here on those on the top. Oops. So it's this expression. So no more division by 0. And so this expression actually has a very interesting intuitive meaning. So if you think of this again as a neural field voting for something by its projections, then what every location phi prime in that field votes for is, with its current threshold firing rate or activation level, is it votes for a little forcelet that has the shape phi minus phi prime. So that will be with a negative slope in front. So that will be a little linear function that has its 0 crossing at phi prime, and its slope is the activation at that level. So rather than vote for a value, you vote for a little attractor. That does the trick. Now, it doesn't have to be exactly this form. There, for instance, you could say, maybe I'll not take a linear function here. I'll take a little range limited, like with an exponential range limitation. It will be determined by the weights. And in some of our implementations, we use different versions for that. And you think about reflexes, they have a more complex structures. They're not exactly linear functions like that. They have some threshold in there and so on. So this is what happens here on this robot. I don't know if you hear the music. There is music playing in the video, but maybe it doesn't go through the Zoom thing. I don't know that. So there's a loudspeaker here in this office somewhere inside. Actually, right now, the robot here in the microphone, so the keyboard was just put on top. There's a screen here for us to monitor what happens. And right now, the sound is actually echoed here off that wall. And that's why the robot has moved here. Let's maybe go back a little bit. See right here, it turns left because there is this echo. Sorry, because there is this echo. And then as it moves on, the echo isn't stable. If the angle to the wall changes, the robot will lose the echo, and it ultimately locks onto the sound coming out of that room, and it goes here through the door. It does actually obstacle avoidance to get through this door, and it goes inside. It also, these are obstacles, and that helps us to navigate that around. So it ultimately ends up here in front of the vehicle. We also had a control of the speed, which I don't explain here, why it actually stops here in front of that loudspeaker. Yeah. So this is a demonstration that the field does provide sensory information about objects in the world. The object is the sound source, and it can actually control behavior. So it is actually compatible with control, compatible with sensory estimation. So that's sort of our overall arching theory, that we are using a language in which decisions can take place: selection, detection, memory, and you will see much more complex decisions. But the language is such that it can always link to the sensory and the motor surfaces. So that concludes that embodied part. Ironically, I only presented that on the second day. And I'll be happy to take questions about that. What I want to do is switch now to real cognition, higher cognition, right? To say, okay, this is all still very low level sensory motor. How can we get to this? Is to actually do some kind of thinking. Yeah. And the next 2 days are really